Okay, welcome everyone to this week's QTFMS talk. This week we are pleased to have Eric Sharpe from the Virginia Tech University. He's going to talk about the notion of decomposition and the generalized symmetries and gauge theory multiverses. Eric, thanks a lot for accepting our invitation. It's a great pleasure to have you with us in this series. You can take it away.
All right, well, thank you all for having me. As was mentioned, the title is Generalized Symmetries and Gauge Theory Multiverses. And as you can see from the list of papers at the bottom, I have been working on this for way too long, I think would probably be a safe assessment. So recently, there's been a lot of interest in what are called generalized symmetries. What I want to do today is outline some basic aspects of those symmetries. And one particular phenomenon, especially, we'll see that sometimes local quantum field theories with generalized symmetries can be equivalent to disjoint unions of other local quantum field theories, which in this context will be known as universes. So this gives rise to some notion of multiverses and gauge theories, which is fun to play with, and no doubt part of the reason I've got a bunch of papers on the subject. So this notion that a local theory, in these circumstances, a local theory with a symmetry is equivalent to a disjoint union, this is what we call decomposition. And explaining this is really going to be the goal of this talk. All right, so let's begin with a quick review of ordinary symmetries, and then I'll talk about the generalized symmetries that are going to be relevant, and then I'll start marching through some examples. So first, let's just recall classical physics, just as a quick grounding point. A group defines a symmetry of a theory if the action is invariant, and this leads to Noether's theorem and notions of conserved currents, as was worked out over 100 years ago now. So in quantum mechanics, we can also express this. Given some group G, we can represent elements of G by unitary operators that respect the group law, that the product of two operators corresponding to two group elements is the same as the operator corresponding to the product of the group elements. This relationship right here. Uh, We say this is a symmetry if this commutes with the Hamiltonian in the sense that, well, in this sense here, or in terms of the infinitesimal operators, if the infinitesimal generators commute with the Hamiltonian in that sense. Now, a simple common example involves gauge transformations in electromagnetism. So here, physically, if A is the gauge field of electromagnetism, then gauge transformations just take this particular form. A is equivalent to A plus d alpha for alpha any function, and we think of it as a gauge transformation. We think of it as a symmetry because both A and A plus d alpha define the same electric and magnetic fields. That alpha here describes an infinitesimal action of the gauge group U1, and since we're identifying fields related by that action, we say that we've gauged the symmetry. Now, how can you generalize this?
Can I
So
have something?
one, please do.
Okay. So like in Chern-Simons, where Hamiltonian is trivial, can we again use the conjugation of the Hamiltonian to say that it is a symmetry?
Oh, it's you're thinking of this statement down here.
Yes.
Yeah, I'm being sloppy. In Chern-Simons theory, one would have to think a little bit more carefully about how to properly define a symmetry, and I don't have a good set of details at my fingertips. I'm here. I was just trying to be just give a general story, but yeah, for Chern-Simons theories, for that matter, for topological field theories, describing the symmetry in terms of operators commuting with Hamiltonian is a little bit tricky because in Chern-Simons theory, or for that matter, in a topological field theory, the Hamiltonian is trivial. So, yeah, this statement and this statement aren't so meaningful. Um, yeah, it's a fine question. Suffice to say that in topological field theories, the correct statement is a little bit more complicated, but I don't want to get bogged down in that.
Okay, I see.
Sound
Thank you.
good?
Yeah.
All right. Okay, let me just
Can
right.
I also ask a question about the
Go for
previous
it.
slide?
Okay.
So here we say that alpha can be any function, but if we consider like compact gauge fields, it should obey some certain, should it obey some
Oh,
certain quantization conditions, or can it still be
um,
anything?
if we're just working infinitesimally, so it depends. If this is just describing the infinitesimal action, then the trick is that the Lie algebra of U1 is just the reals. And so I don't have to work so hard. If I want to describe a global gauge transformation, then indeed there is going to be some integrality condition arising from the fact that the gauge group is U1 rather than the reals. But yeah, fair enough. Here, what I was written was just intended to be some statement about an infinitesimal group action. So that alpha is really
Okay.
in the Lie algebra of U1, so it's just the reals.
Okay, so these are just the small gauge transformations and not the
Yeah,
large gauge transformations. Okay.
exactly. Yeah.
Okay.
Right. So how to generalize this? So one way to generalize the groups appearing, one way to generalize ordinary groups is to go to what are sometimes called higher groups. So a higher group is a lot like an ordinary group, except that you weaken some of the axioms. And one of the standard examples is to weaken associativity. So in a group, we require that when we take a product of three group elements, we don't care where we put the parentheses. G1 times G2, G3 is the same as G1, G2 times G3. Now, in a higher group, all you require is a weaker statement that these two products be isomorphic to one another, with isomorphisms satisfying some commutative diagram of this form here. And in general, in a higher group, one will also weaken other aspects, but I think weakening associativity is one of the key ingredients. We can talk about strict two groups, ordinary two groups, but weakening associativity is common regardless of the details of which particular higher group presentation you work with. So this is one game you can play. And we see examples of this in physics. Here's a simple example. Let's consider the B field. So it's a two-form tensor field potential with a gauge invariance, much like that of electromagnetism. B goes to B plus d lambda, where lambda we can think of as a U1 gauge field. Now here, the gauge transformation itself admits gauge transformations. A gauge transformation by lambda is the same as a gauge transformation by lambda plus d alpha. So as a result, in this case, we can't really talk about gauge transformations being the same. All we can do is require gauge transformations to be isomorphic to one another, so that associativity only can hold up to isomorphism. And it should be said, the B field and fields like this, other tensor fields, potentials, are common in string theory. They pop up all the time, which is a good clue that this is going to be something that will happen a lot. Now, these structures may seem obscure, weakening associativity, higher groups, but they've been known in various circles for a long time. So, for example, in mathematics, mathematicians have been studying higher groups since at least the early 70s. B fields, the more general tensor field potentials, arise in supergravity. So, at that level, they've been seen in physics since the early 80s. The string 2 group is a particular concrete example of a higher group that's been known in elliptic genus circles and has been studied since, at least the mid 80s. And then another version of this, which is going to be more relevant to today's talk, is two-dimensional gauge theories with trivially acting subgroups. We're going to see later that these also are good examples of physical theories with a higher form symmetry. Now, recently, let's say over the last decade or so, this notion of generalized symmetries has become very popular. There's a 2014 paper of Gaiotto et al., which seems to have lit a fire under many people. And as of earlier this month, it has over 1,500 citations, which gives, that's some measure of its popularity. Now, what I'm going to do next is to specialize to two-dimensional gauge theory examples, because they'll be, well, examples with higher form symmetries, but there'll also be good prototypical examples of decomposition in action. So let's consider a theory of electromagnetism, a U1 gauge theory, in which all of the matter fields, all of the electrons, have charges that are multiples of K, so that at least mathematically, a Z mod K subgroup of U1 acts trivially. Now, the first question to ask is, why do I care? Why is that different from a theory in which everything has charges that are multiples of one? Can't I just rescale the charges? Why can't I just, what if, back when electromagnetism was first being developed, what if people had declared that the unit of charge was 5 rather than 1? What does it matter? Well, the answer is that perturbatively, you can certainly rescale like that. But non-perturbatively, you have to be a little bit more careful. And you can get different theories depending upon how they're defined non-perturbatively. So one option to try to see the difference, or another option to see the difference, is to add some heavy, minimally charged fields with masses above the cutoff scale. Now, if you have minimally charged fields, that's certainly going to distinguish, or heavy minimally charged fields will distinguish the cases. If their masses are above the cutoff scale, they're mostly invisible, except that you can still detect them via the periodicity of the theta angle. And the point here, I don't want to spend a lot of time elaborating it, but the point here is simply that in 2 dimensions, the theta angle acts like an electric field. So if you try to build a capacitor in 2 dimensions, by making the capacitor bigger and bigger, at some point the capacitor will short out. The vacuum will generate, a particle-antiparticle pairs will be spontaneously produced from the vacuum just as soon as the energy is of the same scale as their rest mass. And so you can, and that spontaneous production is related to the periodicity of the theta angle. As soon as you break that capacitor, that's telling you the electric field can't be increased anymore, and that effectively determines the periodicity of the theta angle in 2 dimensions. So the upshot is there's a non-perturbative difference between cases in which between these possible charges. I can make sense of a theory with non-minimal charges non-perturbatively, but perturbatively they really are identical. There's no difference between them there. So this theory, in which the charges are multiples of k, has a generalized symmetry that acts on the bundles or the instantons of the U1 gauge theory. I should say for this talk, when I talk about instantons in 2 dimensions, what I'm really going to mean are bundles. In different contexts, sometimes people will mean something different by instantons. But today, when I say talk about an instanton in 2 dimensions, I'm going to use that interchangeably with a bundle. Now there's an action of on the space of bundles on the non-perturbative sectors. Given any one bundle, we can tensor it with a Z mod k bundle for any zk bundle. And if all of the fields have charges that are multiples of k, then this is going to be a symmetry of the theory. So ordinarily, if I change the instanton number, then, okay, I can, evaluate I can expand the action around the instanton background, but there'll be different numbers of zero modes of fields. The expansion will look different depending upon what instanton number you're in. And so in particular, the different instanton sectors will contribute differently to the path integral measure. The point here is that in a theory of electromagnetism in which the charges are multiples of k, this particular operation won't change the non-perturbative sectors. The path integral will be invariant under this particular interchange.
Can I ask a question about
Go
this?
for it. Uh-huh.
Should we think of F tilde as a two-form ZK gauge field, or
Yeah, I'm being I must confess I'm being sloppy when I write this particular expression because indeed for a ZK bundle I cannot write down any sort of de Rham cohomology element that's going to represent the curvature of that Z mod K of that. So this is a lie. That's you're absolutely right. I can't really make sense of this concretely, but oh golly. You sort of you've placed your finger on a sore point. There's any number of papers on generalized symmetries where people will write things like this, and it's what should I say? I fully appreciate that the idea is to represent this, and I agree with the I agree with it as a pictorial level. I can't actually do this concretely, but for some people, this expression makes it a lot easier to think about expressions like this. I guess it depends upon, how you grew up.
So this is kind of like uplifting the ZK field to a U1 field with constraint holonomies.
Yeah, you
Is
could do
that
it
what
that
you're
way.
referring?
You could
Okay.
do it that way. You
Okay.
could embed the Z mod K bundle. That's right. You can embed the ZK. That's a somewhat better way to do it. You could embed the ZK inside a U1. Or what's really going on here is I'm embedding the ZK. Another way of thinking about this is I'm embedding the ZK inside the U1 with some prescribed holonomies that determine which ZK bundle it is that's sitting inside there. If I do that, then I could write down the curvature of a U1 bundle and actually make sense of that. That's exactly right.
I
Or I could
see.
just look at the level of transition functions, take the transition functions for this bundle, and multiply them by some phases valued in kth roots of unity. That would work too.
Okay. I see.
So this is going to be some sort of symmetry, but it's different from the usual symmetries. Ordinarily, when we have a symmetry in physics, we think about a symmetry that acts on the field. Like we have a scalar field theory and we like a complex scalar, and we imagine rotating it by phases. Here, this is a symmetry acting on the non-perturbative sectors. So it's a weird symmetry. Moreover, because it's the way it's acting, we should note that it's an action not of an element of zk, but rather a z mod k bundle that is interchanging the non-perturbative contributions to the quantum field theory. Now, as a result, so first off, it's some sort of symmetry, but because the symmetry parameters involve, or because the symmetry involves an action by a bundle, the symmetry parameters, so to speak, have gauge transformations. So associativity only holds up to isomorphisms. If I multiply two bundles together, the result will be we can talk about the result being isomorphic to a third bundle, but there's not really a good notion of same. The upshot is this is an example of a generalized symmetry, which, depending upon where you grew up, will be denoted by either this or this. I think this notation is often appears in, this is the notation that gets used by mathematicians, and it's what I'm going to tend to use. This notation also gets used if you're going to, especially if you're going to describe generalized symmetries of different degrees. Okay, so far we've seen that a gauge theory with a trivially acting subgroup has a generalized symmetry that interchanges the instanton sectors. Let's try to characterize these symmetries a bit more precisely. So let's consider, or let's first go back to Noether's theorem. Consider an ordinary global symmetry. Under an infinitesimal symmetry parameterized by alpha, or under an infinitesimal action parameterized by alpha, we can say the action goes to S plus the integral of d alpha wedge j, would be one way of expressing it. And then j is the Hodge dual of the usual Noether current. It's a d minus 1 form, and it obeys dj is equal to 0. This is the expression of the conservation law in terms of this language. Formally, we can associate an operator supported along some submanifold, which just looks like the exponential of the integral of j. And it's invariant under deformations of M because J is closed. So this is an example of what's sometimes called a topological operator, associated in this case to an ordinary symmetry. It's an operator that lies along some real codimension 1 submanifold inside the space. Now we can generalize this as follows. Let's consider another global symmetry, but now let's parameterize the symmetry by a p-form. And for finite groups, this isn't going to be a great description, but just at some pictorial level to try to get some to try to get some sort of concrete handle on how to describe this, this will work. So now, if our global symmetry is changing the action like so, global because if alpha is constant, then this stuff goes away. If alpha is a p form, the conserved current we get is a d minus p minus 1 form, which again is closed. And we can associate an operator which is now supported along a submanifold of dimension d minus p minus 1, or codimension p plus 1. And again, it's invariant under deformations because of that conservation law. We call this a p-form symmetry, or this is one description of p-form symmetries that's often bandied about. In this language, ordinary symmetries involving ordinary groups are zero-form symmetries. And the example we discussed a couple of minutes ago, a gauge theory with a trivially acting subgroup, this has a one-form symmetry, what I'm usually going to denote as a BK symmetry in this talk, where K is meant to be the trivially acting subgroup. All right, now sometimes these generalized symmetries can have exotic effects, and this is really going to be the thing I want to focus on for the rest of this talk. In d dimensions, if a local quantum field theory has a global d-1 form symmetry, then it's equivalent to a disjoint union of other local theories. So these subtheories are known as universes, and this is what we call a decomposition. When this happens, we say that the field theory decomposes, and this is a somewhat exotic phenomenon at the level of field theory, so we can use this to get some insight into the properties of the theory and some insight into quantum field theory itself. And I'm going to be exploring that in the rest of this talk. So here's a prototypical example of decomposition in action. Let's consider a two-dimensional gauge theory with a trivially acting central subgroup. So the U1 gauge theory I mentioned earlier, in which all the matter has charge K, would be an example of this. The claim of decomposition is that this gauge theory is equivalent to a disjoint union of order K copies of G mod K gauge theories, each with a possibly different theta angle, which might be discrete. So schematically, the original gauge theory is really equivalent to a sum of other theories, like in a Moiré pattern, where you take two screens and sort of slide them across one another. The Moiré pattern itself looks very complicated, but it's really just built out of superimposing two simpler objects. That's the idea of a decomposition. So why is the existence of such a thing surprising? So to explain, let me take a minute to distinguish a sum of field theories from a product of field theories, because one of these we work with all the time, and the other doesn't pop up so often at all. Let's consider two quantum field theories, 1 and 2, with path integrals like so. So ZT1 is one of them with action S1, Z22 is the other with action S2. In a product, we multiply the partition functions. The partition function of T1 tensor T2 is just the product of the partition functions, and then we can just add the actions. So for example, if I have a scalar field theory with two free scalar fields, that's a good example of a product. A scalar field theory with two free scalar fields we can think of as a product of a field of two copies of a field theory with one scalar field. The action for the whole thing is just the sum of the actions for the two theories separately. A sum is different. In a sum of theories, we add partition functions. So I'm being a little bit sloppy. I'm assuming that the underlying spacetime is connected. If it isn't connected, there's a more complicated version of this. So for simplicity, I'll assume that the underlying spacetime is connected. Then the partition function of the sum of theories is a sum of the partition functions. So it's a sum of these path integrals. Now, if we have a sum, there's no way to write this in terms of a single action ordinarily. I mean, on the face of it, this would require something crazy in algebra. We'd need the log of the sum to be the sum of the logs naively, which of course is just not true. But in special cases, one can arrange for that to happen. And this is what happens in a decomposition. Phrased another way, there's some issue with locality that's lurking in the background here. The reason we don't usually talk about a sum of theories is that you can't ordinarily, it's not easy, it's not obvious how to write down a single local action for a sum of theories. You can write down actions for each of them separately, but for the whole thing, not so much. In a decomposition, part of the reason that decomposition is surprising is that you can write down a local action which is describing a sum of theories in this sense. So it's a neat trick. It's one of the reasons why that's a neat trick. So what does it mean? How can you tell if one local theory is a sum of other local theories? Well, one thing you need is there needs to be some projection operators that project onto those two different components, those two different subtheories. So we need the theory to contain topological operators, topological projection operators. that are orthogonal. Well, if different projection operators are orthogonal in the sense that their product is zero, the product of a single projection operator with itself is just itself back again. We also need them to be complete. The sum of the projection operators has to add up to one. Everything, every state in the theory needs to project somewhere. And we need these projection operators to commute with the other operators. So a set of operators of this form are simultaneously diagonalizable since they commute with one another. And the total state space can be written as a sum of the state spaces for each of the constituent subtheories, each of the constituent universes. So in the language of extended objects from earlier, a d-1 form symmetry in d dimensions has operators supported along dimensions of submanifolds of dimension d minus p minus 1, which for p equals d minus 1 is d minus 1 minus 1, which is 0. And basically, those operators construct the projectors up here. These projectors are built out of those, well, quote unquote, extended operators, which are actually zero-dimensional. In the case of gauge theories with trivially acting subgroups, because the action of that subgroup is trivial, the operators corresponding to that commute with everything, and that's part of why they diagonalize the state space. At the level of correlation functions, if I take some random correlation function in the original theory, and if the original theory has projection operators like this, then I can insert a copy of 1. I can use the fact that the operators are complete to just plug in a 1 there. And then because the projection operators are orthogonal and commute with the other operators and square to themselves, I can write each of these. I can multiply these pi i's out and commute them to multiply each of these separate operators, and then write the original correlation function as a sum of correlation functions, now where each of these is evaluated in a separate theory, given by projecting each of these O-twiddles is the projection of an operator of the original theory onto the state space or into the operator space of the constituent subtheory. So that's one property, one thing you can look for if you want to test whether something decomposes. An easier test you can do, of course, this doesn't suffice, but it's usually much faster, is to check whether the partition functions decompose. Formally, a partition function is some sum over states of the exponential of minus beta times Hamiltonian. If there's a decomposition, we can decompose a state space into a sum of universes and then a sum within each universe. And so the partition function can be written as a sum of partition functions from constituent universes. So let me go back to a more concrete example, or let me list a few examples. Finite gauge theories in two-dimensional orbifolds. The common thread will be a subgroup of the gauge group acts trivially. Suppose, for example, if K is a subgroup of the orbifold group, and for simplicity, let's suppose it's a subgroup of the center that acts trivially, then an orbifold by the big gauge group gamma is going to be the same as a disjoint union of orbifolds by smaller subgroups in which we quotient out that trivially acting piece. There are also analogs in gauge theories. A two-dimensional U1 gauge theory with non-minimal charges, of the sort I outlined a few minutes ago, is the same as a sum of U1 theories with minimal charges. So this is in some contexts called the charge P Schwinger model, if all the fields have charges that are multiples of P. Another example, suppose I have a two-dimensional gauge theory with center invariant matter. That's going to be the same as a sum of G mod ZG gauge theories, where ZG is the center, with discrete theta angles. So for example, an SU2 theory in two dimensions with center invariant matter is equivalent to the sum of a pair of SO3 theories with different discrete theta angles. For another example, two-dimensional pure Yang-Mills theories is the same as a sum of trivial theories indexed by irrep sub G. Here, the entire gauge group acts trivially. So if we quotient out the trivially acting group, we're left with nothing. We can write the pure SU2 theory in two dimensions as a sum of sigma models on points indexed by the irreducible representations of SU2. And then it's more obscure, but there are also versions in two-dimensional non-invertible orbifolds, which have been worked out relatively recently. And then there are higher dimensional examples. So in three dimensions, we could talk about a three-dimensional Chern-Simons theory with a gauged, non-effectively acting one-form symmetry. This turns out to be a disjoint union of ordinary Chern-Simons theories, and along the boundary, this will reduce to a two-dimensional decomposition. We could talk about three-dimensional orbifolds by finite, non-effectively acting two groups. This turns out to be a disjoint union of ordinary three-dimensional orbifolds. In four dimensions, we could talk about a four-dimensional Yang-Mills with restriction to instantons of degree divisible by k. I haven't emphasized this perspective yet, but this is another part of this whole story. Many of these theories will also be equivalent to theories with restrictions on the allowed instanton numbers. So in this case, a four-dimensional Yang-Mills theory with a restriction to instantons divisible by k is equivalent to a disjoint union of ordinary 4D Yang-Mills theories, but with different theta angles. And part of what's going on is that when you sum over the constituent subtheories, each of the subtheories has all the possible instantons, but the instantons are weighted by different theta angles. So when you look at the result of summing up everything in the entire theory, what you find is that contributions from instantons whose degrees aren't divisible by k get multiplied by a sum of roots of unity, and so cancel out, fall out of the sum. And then there are more examples. In topological field theories, we could talk about 2D unitary TFTs with semi-simple local operator algebras. These will decompose to invertibles. So very briefly, a two-dimensional abelian BF theory is a disjoint union of invertible field theories. The two-dimensional G-mod G model is a disjoint union of invertible theories. The two-dimensional Dijkgraaf-Witten is a sum of invertible theories. Mathematically, I don't know if anyone in in the audience will care, but this can also be understood, or another example of this is a sigma model on a gerbe. So a gerbe is a special kind of stack. It's a generalization of a space, and I'm not going to be talking about them very much at all, but just in case there's anyone here who's interested in this, if you try to make sense of sigma models on stacks, then sigma models on gerbes are problematic because when you make sense of a sigma model on a gerbe, it looks like the instanton number has been restricted, which usually isn't allowed. But it turns out, by virtue of decomposition, the sigma model on a gerbe is equivalent to a disjoint union of sigma models on spaces with various B fields, and this solves technical issues with making sense of cluster decomposition and such theories. Anyway, let me also distinguish something else. Decomposition is a lot like spontaneous symmetry breaking, but it's different. So in spontaneous symmetry breaking, one has a notion of superselection sectors. So a superselection sector is something like a subtheory, but not quite. The different quote unquote subtheories are only really genuinely disjoint from one another deep in the infrared. If you go to higher energies, then the states will mesh into one another. We can think about this in terms of some sort of domain wall construction. Superselection sectors are separated by dynamical domain walls. In a decomposition, the idea of a decomposition is that the field theories are disjoint at all energy scales. This is meant to be a picture in which the two theories just do not talk to one another. You can't merge them back together by going to higher energy. They're separated by non-dynamical domain walls, and the idea of the universe is that you really have multiple different quantum field theories present. They don't sort of merge into one another if you go to higher energies. The idea really is that they're distinct. So if you go deep to the infrared, superselection sectors can turn into universes deep in the IR, but away from the IR, superselection sectors and universes are different notions.
Can I ask a
So,
question about this point?
sure, go right ahead.
So let's say in a quantum field theory with D minus one form symmetry, we add a deformation that breaks this D minus one form symmetry. So there are no
Mhm.
longer decomposition in universes.
Uh-huh.
Is that going to give us a spontaneous symmetry breaking because they are very similar notions? Or if you break the
Um,
symmetry, what happens in the new quantum field theory after the deformation?
Uh, it depends upon how you break it. I wouldn't expect either one to be honest. But I think the what I really to really answer that question, I want to look at a specific example because I think the answer is going to depend upon
Hmm.
the particular example. So my knee-jerk reaction is that in general, the new theory that you get by breaking that D-1 form symmetry isn't going to exhibit either universes or superselection sectors. Um, but the answer may depend upon, in different examples, you may something more subtle may happen. Um,
Hmm. I mean,
f-
for
so,
example, oh, sorry, you were saying
I
something.
was going to say, if, for example, if you take a two-dimensional, like take two-dimensional pure Yang mills and
Hmm.
add some matter fields that are charged under the gauge group, then in fact, we could do this continuously. Start with, here's an example. Let me do an even easier example. Let's take two-dimensional pure Maxwell theory. So that's a two-dimensional pure U1 theory that will
Hmm.
decompose into a countably infinite union of trivial theories. Now, let's suppose we have some massive fields of charge 1. But initially they're
Okay.
massive. So at low energies, you still think you have some sort of approximate D-1 form symmetry. If you drop the masses of those fields down, then as the masses go to zero, that approximate D-1 form symmetry is less and less of a good approximation. And then by the time they become massless, you no longer have a D-1 form symmetry at all. And then after they
Hmm.
become massless, you've got some version of either QED or a scalar QED, depending upon whether the fields were fermions or scalars. And then in a
Hmm.
QED, um, okay, you've gauged the symmetry, but a priori in a QED, if I really have just massive minimally charged fields, I'm not. Well, there are the charge superselection sectors in QED. So, okay, in that example, you have superselection sectors. But you definitely don't have universes. Um,
Okay.
and then, yeah, again, I think the best answer is we'd have to talk about specific examples. But
Hmm.
in general, off the top of my head, depending upon the example, I wouldn't if you break the D-1 form symmetry, I don't think, I could be wrong. I wouldn't think that you'd get super selection sectors in all cases, but I might be thinking about that wrong.
I see. I mean, what I was trying to think of, imagine was like, since we have uh, probe domain walls in the
Uh-huh.
first case where we have the
Uh-huh.
decomposition,
Uh-huh.
and let's say we deform the QFT in a specific way that in the spectrum there are now dynamical solitons, which are like
Uh-huh.
domain walls.
Uh-huh.
So then we would get the super selection sector. So these non-dynamical domain walls would become dynamical after deformation, so that the universe would become the super selection sector. That's what
That
I
does
was
seem
trying to
like a reasonable
imagine.
argument. I mean that I can't argue with that. But I can't argue with that, but I'm worried that in general it might not hold.
Hmm.
Yeah, that seems like a reasonable enough argument, and I think that's basically what was going on in the QED example I just outlined.
Mhm.
Um, but I prefer to work in examples. I'm always a little bit wary of general arguments because
Mhm.
um, yeah, the problem with general arguments is that there's always a little bit too much, because we're not mathematicians, there's always a little bit too much wiggle room. And these sorts of general arguments are, um, sorry, as an aside, let me pick on no-go theorems. There's a joke in some circles that you should never trust a no-go theorem until after you know some counterexamples. And the reason being someone comes up with some good general argument that seems like it ought to be right, and then someone else will come up and say, "Oh, but wait,
Mhm.
there's this counterexample." I'm always just a little bit wary of general arguments for that reason.
Mhm. Yeah,
Oh,
yeah,
I
I
see a
see.
question in chat. Can a local quantum
Yeah.
field theory always be decomposed as a sum of simpler local theories at different energy scales? I wouldn't think so. But at the moment, I wouldn't think so. In special cases, like in the case of super selection sectors, if you go deep into the infrared, the superselection sectors will become disjoint from one another. In some sense, they'll be universes, but at the same time, I'm not certain if I can write down a local quantum field theory for the deep IR limit either. Um, I'm going to I have lots of examples where decomposition happens, but I personally would not be I personally don't want to claim that you can always decompose local field theory at some energy scale. You may you may well be right. I'm just a little bit leery of making that particular statement. I think it's just too strong, but I could be mistaken. Okay. Any other questions, either verbally or in chat? Okay, let me go on. Examples. I'm running a bit over, so let me just summarize the slide by saying we've done lots and lots of checks in two-dimensional GLSMs and orbifolds. This comes up in open strings. You can see this using supersymmetric localization. You can see this in non-supersymmetric pure Yang mills. There's been some numerical work on using lattice gauge theories. You can play some games with 3D and 4D theories. There's a SimTFT construction if you're interested in such things. Um, and there's also a bunch of applications. The original application was just to make sense of the physics of a sigma model whose target is a generalization of a space called a stack, because the physics of that just did not seem to make sense. And for a while, it just looked like you could not write down a local quantum field theory describing that. It just didn't make sense. There are math predictions. You can use this to make predictions for Gromov-Witten theory and more recently quantum K theory. The Gromov-Witten theory predictions were checked rigorously back around almost 20 years ago now. The quantum K theory predictions are newer and no one's had a chance to check them yet. We can apply them to, my favorite game is to use decomposition to describe, give non-perturbative constructions of geometries and what are called non-commutative resolutions in gauge linear sigma models. I could easily talk about that all day, but I don't know that anyone else here would care. So suffice to say, there's a fun application, but I don't want to belabor it too much. You can use this to understand, say, IR limits of pure two-dimensional supersymmetric gauge theories. A more recent application was to understand the Wang-Wen-Witten anomaly resolution procedure. I may say a few words about that at the end. Okay, so just to summarize so far, in d space-time dimensions, a theory decomposes if it has a global d-1 form symmetry. So let me walk through a little more detail some simple examples. Suppose we have a G-gauge theory in 2 dimensions, where G is some semi-simple gauge group like SU2, with some finite central subgroup acting trivially. For reasons discussed earlier, this has a one-form symmetry. Basically, I can take the instantons, the bundles in this theory, and tensor in K bundles, and without changing the path integral. It just it leaves the path integral invariant. Now, so far, this sounds like just one quantum field theory. But what I'm going to do is outline some of the consequences of decomposition and see how this is actually the same thing as a sum of other quantum field theories. So first off, what are the projection operators? So briefly, the projection operators can be understood as, well, twist fields or Gukov-Witten operators, enumerated by elements of the center of the group algebra. Existence of those projectors is ultimately a consequence of something called Wedderburn's theorem. It's technical. I don't want to get into that too much. Let me say a few words about partition functions. So to understand partition functions, let me give a more precise statement of how decomposition works in this example. The statement here is that a G-gauge theory with a central K is the same as a disjoint union of G mod K gauge theories with different discrete theta angles. And the prototypical example is to write an SU2 theory as a sum of SO3 theories with different discrete theta angles. Now, perturbatively, SU2 and the two SO3s are identical. The differences between these theories are all non-perturbative. This is really a story about non-perturbative effects. Now, for example, The SU2 instantons, the SU2 bundles, or another issue, the SU2 bundles are a subset of SO3 bundles. Um, so you might ask, how in the world can this be the same as this? Because this does not have as many bundles as either of these SO3 theories do. The answer involves these discrete theta angles. These discrete theta angles couple to technically the second Stiefel-Whitney class, which means that they weight the non-SU2 SO3 bundles by signs. So in building the sum of these two theories, if I have an SO3 bundle that doesn't come from SU2, in this theory, whatever contribution it makes to this theory, in this theory, it will make the same contribution but multiplied by a sign. So when I sum these two theories together, I sum the partition functions and the contribution from that non-SU2 SO3 instanton cancels out. So then summing over these two SO3 theories, this disjoint union of two SO3 theories cancels out some of the SO3 bundles, leaving you just with the SU2 bundles. So this is one of the fun games you can play with decomposition, this sort of cancellation effect of instantons between the different components. So formally, if I write the partition function of the disjoint union in this form, the game I can play is I can move the sum inside the path integral, like so. On one hand, I have a disjoint union. Over here, this is really a projection operator that's projecting onto contributions from instantons from SU2 bundles rather that as opposed to SO3 bundles. This you can think of this as a projection operator that's projecting out contributions from SO3 bundles that don't come from SU2. So the disjoint union is performing a projection. So we could also think about this as an interference effect. And I like to describe this as a sort of multiverse interference because it's an interference effect involving the different universes of the decomposition. So schematically, so on the one hand, again, we have a disjoint union, or we have one field theory with a restriction on the non-perturbative sectors. So this is the you could think of this as the SU2 theory, and this is the disjoint union of the two SO3 theories. So schematically, we're combining two theories to form a distinct third. So we have a pair of different SO3 theories, the two universes, which combine to form the SU2 theory via this multiverse interference that's canceling out the SO3 parts that don't make sense in SU2. So a quick consistency check. We can see this directly for pure SU2 Yang-Mills in two dimensions. So at the level of partition functions, from Migdal and Rusakov's work years ago, the partition function of an SU2 theory looks like a sum overall SU2 representations of something like this. This partition function of the SO3 plus theory, the plus discrete theta angle is basically no discrete theta angle at all. This is just an ordinary SO3 theory, and again, it has the partition function has the same form except that we sum overall SO3 representations. Now, about a decade ago, Yuji Tachikawa worked out the partition function of an SO3 theory with a non-trivial discrete theta angle. This has the same form, except that it's a sum over SU2 reps that aren't SO3 reps. Now, if we put these three things together, you can quickly read off that the partition function of the SU2 theory is the sum of the partition function of the SO3 plus theory and the partition function of the SO3 minus theory. So an SO3 theory has more bundles, but fewer representations. For example, the spin representation is not a representation of SO3, but it is a representation of SU2. So in this sum, you don't sum over spins, but this is only a sum over spins and things that don't pop up in SO3. So the partition functions work out as expected, which is a nice consistency check. Let me say a few more words about this instanton cancellation business because there's some interesting field theory going on in the background. Suppose we try to require that the total instanton number always vanish in a field theory. Let's start with a field configuration with no net instantons. This is an old argument due to Weinberg, whom I'll be citing in a moment. So even if we have no net instantons, we can still think about that as a superposition of a closely spaced sort of instanton and anti-instanton. Now, if I move those two things far apart from one another, then locally I have regions of space-time with non-zero instanton numbers. So if physics is local, technically if cluster decomposition holds, then in these widely spaced regions, the theories have instantons. So even if we start with no net instantons, cluster decomposition implies that we should get instantons. Now, Weinberg noticed this back in the 70s, and as a result, stated that all local quantum field theories must sum over all instantons so as to preserve cluster decomposition. So this is a kind of no-go theorem, if you will. Now, as with all good no-go theorems, it has a loophole. Disjoint unions of field theories also violate cluster decomposition for boring reasons, but are straightforward to deal with. So if a theory with restriction on instantons is also a disjoint union of theories which are separately well behaved, then all is good. There's no contradiction. And that's part of what's going on in a decomposition. So I'm running a bit short on time. There's a fun statement that can be made about Wilson lines and understanding of his defects linking different universes, but I think I'm going to skip that for lack of time. There are many different consistency checks, as I mentioned back at the beginning. For example, we can look at mirrors to the supersymmetric CPN model, but again, I'm running a bit short on time, so
By
if
the
someone's
way,
curious,
we don't have a time limit, so if you want to
oh,
go on, we are fine with listening to these things.
oh, okay. Well, in that case, if you guys are, I don't want to, I don't want to waste too much of everyone's time, but in that case, good. I
Usually our
will.
talks are more than 1 hour.
Okay,
So
perfect, perfect. Excellent. Then I will delve into some more of these details. All right, let's take the supersymmetric CPN model. So the supersymmetric CPN model is a two-dimensional supersymmetric U1 gauge theory with n plus 1 chiral superfields, each of charge 1. Semi-classically, the Higgs moduli space of this U1 gauge theory is just CPN. We think about the chiral superfields as being like homogeneous coordinates on a projective space. Quotienting out the U1 recovers the original projective space. Now, the merit of this theory is a supersymmetric Landau-Ginzburg model with a superpotential of this form. This was worked out by Hori and Vafa. Actually, I think it goes back to Toru Oguchi sometime before them, but certainly it appears in Hori and Vafa's mirror symmetry construction. And the mirror encodes the non-perturbative physics of the original theory as some sort of classical or perturbative physics in the mirror. This Q, for example, well, it goes to zero classically. This Q is some measure of the quantum corrections, and the upshot is by doing classical computations in this Landau-Ginzburg theory, one can recover the correlation functions of the A-twisted supersymmetric CPN model. So how does decomposition work in this case? Well, let's consider a variation of the supersymmetric CPN model. Consider a two-dimensional supersymmetric CPN model in which the fields have charge k bigger than 1. So this goes back to the example I mentioned at the beginning, where we have a U1 gauge theory with fields of charge different from 1. Now, for reasons discussed already, if I have a U1 gauge theory with fields of non-minimal charges, then that theory has a one-form symmetry because there's some trivially acting Z mod k, and so I can play funny games with permuting the U1 bundles. Now, decomposition predicts that because of that BZK one-form symmetry, this decomposes into k copies of the ordinary supersymmetric CPN model. And we can see that in the mirror. So the mirror can be computed. Briefly, you get a superpotential that looks like this. It's almost the same as the superpotential up here. The novel part is this bit I'm circling, this upsilon. This is a Z mod k valued field whose values the path integral sums over. Now we interpret that path integral sum as summing over the contributions from different universes, or phrased another way, what does it mean if you have a discrete valued field? What it means in this context is that each value of the field represents a different universe. So we have a sum of copies of the mirror to the supersymmetric CPN model, in each of which the superpotential has been modified slightly. So this Q that encodes the theta angle of the original gauge theory gets shifted slightly. So in effect, in each of these copies, theta is shifted by some fraction of a circle, which is what we would expect for a decomposition. So anyway, this is how you can see decomposition in U1 in supersymmetric U1 theory. This is an example of how you can see decomposition in mirrors. So in passing, ordinarily, I describe decomposition in terms of universes with variable theta angles or B fields or complex scalar parameters. In this particular mirror, in the mirror, these become complex structure parameters. So the mirror to a decomposition involves, again, a sum of universes, but now with variable complex structures rather than variable theta angles or variable B fields, which is a neat trick which honestly, I have not had the time to explore, but I keep meaning to circle back around to one of these days when I can find the time. All right, now let me tell you, let me build up to real gauge theories, which will, well, describe some more recent work. So here's a fun fact. If we gauge a p-form symmetry in d dimensions, the gauge theory has a quantum symmetry, a d minus p minus 2 form symmetry, with the property that gauging it returns the original theory. So the prototype of this was worked out in 2 dimensions back in the 80s by Vafa, who noticed that in orbifolds, a G orbifold, at least for G abelian, has a rep G zero form quantum symmetry. Now, Vafa back then was just working in 2 dimensions with ordinary symmetries, and also G was abelian because only for G abelian is rep G an ordinary symmetry. But nowadays we understand how to generalize this quite a bit. Now,
Can I
what
ask a
happens?
question?
Please
It's
do.
a bit like detail, but by
Mhm.
gauging we mean like a flat gauging, right? Because if you
Yes,
gauge
yes,
dynamically,
yes.
then
That's
that's not going
exactly
to
it.
happen.
That's
Yeah.
exactly it. I was going to suppress that level of detail, but you're exactly right. This is going to be a
Okay.
flat gauging, a topological gauging.
Okay.
Yeah, in Vafa's example, Vafa was working with orbifolds for which G was finite, so
It's
there was
already
no
flat
difference. But
always.
you're absolutely right. But that for the most part, I was going to suppress that level of detail just because there's
Okay.
only there's I can only say so much in an hour. But you're right. In general, the
Yeah.
quantum
Okay.
symmetry that's right. It's a flat gauging.
Okay.
Right. So what happens in decomposition? Well, if in decomposition, we have a theory with a global d minus 1 form symmetry. If we gauge that d minus 1 form symmetry, the result is a single universe, which makes sense. The decomposition is a result of having a d minus 1 form symmetry. If we remove the d minus 1 form symmetry from the theory by gauging it, the theory sort of falls onto one of the universes. Which universe depends upon a choice of theta angle, which I'm suppressing in this discussion. Now, when we do that, the quantum symmetry you get, well, from what I've just told you, it's a d minus p minus 2 form symmetry. But if p is d minus 1, that's a d minus 1 minus 2. And with a little bit of algebra, you see that's a minus 1 form symmetry. So minus 1 form symmetries are linked to decompositions. Now, what in the world is a minus 1 form symmetry? Maybe let me not try getting into that because answering that question, I'm not certain I can give a completely good answer to what a minus 1 form symmetry is. But what I can say is that for a minus 1 form symmetry, the corresponding extended objects are going to be space-time filling. If you think about the dimensions of the charged objects for p-form symmetry, if p is minus 1, then the charged objects you get fill the entire space-time. And the logic here is that if you then gauge the minus 1 form symmetry, then in principle what you're doing is recapitulating the decomposition. So in general, if you gauge a quantum symmetry, you get the original theory back again. The same thing is going on here. If I start with the theory that decomposes, I can gauge the d minus 1 form symmetry to get something with a minus 1 form symmetry. If I gauge that minus 1 form symmetry, well, to do that, I'm going to have to sum over these space-time filling objects. that will recapitulate the decomposition. And so I can sort of go back and forth between a decomposition and a -1 form symmetry just by gauging them. So decompositions and -1 form symmetries go hand in hand with one another. Now, many, not all examples of decomposition in two dimensions fit into a pattern like this. There are more complicated examples, but to make the talk finite, let me specialize to examples like this for a second. So I have in two dimensions, suppose I have a G-gauge theory with a trivially acting H1 form symmetry. So I need the matter to be invariant under H. Then it's this disjoint union. If I gauge the D-1 form symmetry, then I get one of those G mod H gauge theories, but with a -1 form symmetry. If I now gauge the -1 form symmetry, I get back here. So I can just loop back and forth between decompositions and universes by gauging D-1 form symmetries and -1 form symmetries. Um, Now, recently, motivated by a number of works, we've started looking at continuous families. Years, I've mostly been focused on, well, I've only been focused on decompositions in which there were, well, initially finitely many universes, and then somewhat more recently, countably infinitely many universes. But up until recently, I've only really thought about decompositions with um, you know, discrete, discretely indexed universes. Very recently, just in my most recent paper on the subject, we started looking up at theories in which you have continuous families of universes. So let's consider, for example, two-dimensional U1 theories versus two-dimensional real gauge theories. So to understand what I'm going to do here, let's start with an ordinary U1 gauge theory in two dimensions with some matter fields with some charges, which I'm mostly not going to specify. What happens if I replace the gauge group by the reals? Reals act in a similar fashion. I take one of the fields, I multiply by a phase, which looks like e to the q alpha, but where alpha is now an element of the real numbers. So, if I really take this seriously, if this R is now the gauge group, not just some Lie algebra, then under this action, there's a trivially acting subgroup that the integers form a trivially acting subgroup of the reals. So if I have a trivially acting subgroup, I expect a decomposition. And here I expect the decomposition should be into universes indexed by, well, representations of that trivially acting subgroup. But the representations of the integers is a circle. So up until this point, I've only thought about decompositions into discretely many universes. This is, on the face of it, a decomposition into a continuous family of universes. Each of those universes should be an R mod Z or a U1 gauge theory. So what I'm claiming in this context is that a real gauge theory, at least a real gauge theory with matter transforming like this, is equal to a disjoint union of a circle's worth of U1 gauge theories. So it's a little bit confusing. There are two different circles. There's the gauge group of each of these gauge theories, but then I'm parameterizing them also by a circle as well. This S1 is not the same as that U1, but it's just two copies of, well, hopefully you see what I mean. Now, how to interpret that S1? So briefly, the answer is in terms of theta angles. So theta angles act as quantum -1 form symmetries, which are dual to that integer 1 form symmetry. And here, really, I should talk about topological gauging rather than continuous gauging. Again, I'm going to sweep that detail under the rug. But the picture in this most recent example is that we can relate U1 gauge theories to real gauge theories by gauging either a U1 -1 form symmetry or a Z1 form symmetry, depending upon which direction you want to go. And there appears to be a bunch of fun games you can play with this. So, for example, let's look at the partition functions. Let's write the partition function of a U1 gauge theory as a function of its theta angle in two dimensions in this form schematically. So it's some sum over first-term classes of bundles of contribution to the path integral measure weighted by the theta angle. This is just meant to be a very schematic formal picture of the partition function. So now if I integrate over theta angles, well, I exchange the integral with the sum as I tend to do since I'm a physicist, then okay, the integral of that is basically a Kronecker delta function that forces n to be 0. So on the face of it, if I start with a U1 theory and topologically gauge this -1 form symmetry, the result should have no instantons at all. And that is completely consistent with a real gauge theory. There are no instantons in a real gauge theory. So I mentioned earlier we can get a restriction on instantons in a decomposition. This is the extreme limit of this. We can remove all the instantons in a local quantum field theory, which is just really uh, pushing the I mentioned Weinberg gave reasons why one should always sum over all instantons. This is really pushing hard against Weinberg's no-go statement. So let's look at this in an example. Let's take the supersymmetric CPN model. Now, ordinarily, for a gauge group, if the gauge group is U1, there's an anomalous axial R symmetry. And depending upon your backgrounds, you may not all be familiar with this. I don't know. But for those that are, in the supersymmetric CPN model, there is an anomalous axial U1R symmetry, I'll denote by U1A, which has some non-anomalous subgroup. There's a Z mod 2n+1, actually. The rest of it has an anomaly. If we replace the U1 by reals, the analog of the supersymmetric CPN model with gauge group the reals is anomaly free because it's anomaly free. The anomaly here only exists if you have a U1 gauge theory. Now, how can that be consistent? If we have how does that make sense? On the one hand, the real gauge theory is supposed to be a disjoint union over a circle's worth of U1 gauge theories. How can we reconcile the fact that one has an anomaly and the other doesn't? So here's the picture. Here's the U1 axial anomaly. Here's the anomaly-free subgroup. In a single U1 gauge theory, this coset that I'm labeling U1 motion is totally anomalous. In the real gauge theory, the S1 parametrized family of U1 gauge theories, this U1 motion just rotates between the universes. So remember that ordinarily if you have just at the level of field theory, if I have a theta angle and an axial symmetry, the theta angle usually isn't meaningful because rotating by the axial symmetry will change the theta angle. Here, the theta angle is parametrizing different universes. So if I act by this anomalous symmetry, I'll rotate the theta angle, but rotating the theta angle is rotating between the different universes. So altogether, in the real case, this U1 axial is essentially non-anomalous. There's this subgroup, which is definitely non-anomalous, but the rest of it is just rotating the universes between one another, which is why in the real gauge theory, the axial symmetry is not anomalous. But if you fix any one universe, if you just stick to a single U1 gauge theory, this U1 motion is anomalous. Okay. Some other general comments. I'm about 10 minutes over. I can probably go on for another 10 or 15 minutes. If at some point this gets tiresome, please don't hesitate to interrupt me. I won't be offended. I'm already 10 minutes over time by my count, so I'm happy to keep going. But when you guys get tired, don't hesitate to tell me to stop. It's all good. Let's talk about pure two-dimensional gauge theories for a second. A 2D pure gauge theory is equivalent to a disjoint union of what are now called invertible field theories. These are field theories with whose state space contains a single element. It just contains a vacuum, nothing else. They're pure counterterm theories in some sense. In the case of a pure two-dimensional U1 Maxwell theory, this is a disjoint union of invertible field theories indexed by the charges. This is a special case of some old story. It's a little bit obscure in some quarters. That abelian gauge theories have superselection sectors determined corresponding to the total charges. In 2 dimensions, a charge is like a domain wall. If I try to build an operator for a charge in 1 + 1 dimensions, well, there's Space is only one dimensional, so if I put the charge somewhere, it's blocking space. So charges act like domain walls. If I have a pure two-dimensional U1 gauge theory, those charges are non-dynamical, or those domain walls are non-dynamical and separate the universes. So the usual story that a U1 gauge theory has superselection sectors corresponding to charges. In the two-dimensional pure Maxwell case, those charge superselection sectors actually become universes. Now, in the case of a two-dimensional real Maxwell theory, a two-dimensional pure real gauge theory, we expect a similar story, but now where the invertible field theories are indexed by representations of R, which is R back again. So we expect a continuous family of invertible field theories. So let's see how this works. For the two-dimensional U1 Maxwell, we can write the partition function explicitly in this form. To get the corresponding real gauge theory, we can topologically gauge that theta angle, which means we basically just integrate over the theta angles. And when we do so, the integral of the sum turns into an integral over the real numbers of this Gaussian, where this quantity r is 2 pi q plus theta in this language. The reason I can combine the theta integral and the sum is really is a detail that's a little bit beyond the scope of this talk. It's an analog of the Witten effect. If you continuously rotate the theta angle in a two-dimensional theory, then you go from continuously rotating the theta angle will move you from one universe to another universe, just like in the Witten effect for dyons in 4 dimensions. Continuously rotating the theta angle will change the dion charge. Something similar happens here with universes. So if we start with the partition function for a U1 Maxwell theory at some general theta angle and topologically gauge that the -1 form symmetry, integrate over the theta angles, what we get turns out to be the partition function for the real gauge theory as expected. So the partition functions work when we try to think about decomposition for this continuous family of universes. All right. So in the time remaining, I think I've said what I'm going to say about real gauge theory. In the time remaining, let me talk about some other examples. Let me talk about a 4-dimensional Yang-Mills theory with a restriction on instantons. This is some work of Tanizaki Unzel from about 6 years ago now. So I'm in 4 dimensions. We've got a 4-dimensional Yang-Mills theory. Here's the action for an ordinary 4-dimensional Yang-Mills theory. Tanizaki and Unzo asked, how can you restrict the degrees of instantons? Well, it's possible to write down a local action that will restrict the instanton degrees. And here's what it looks like. You add a scalar field of periodicity 2 pi and a 3-form potential with curvature h and these terms to the action, so that altogether the action looks like this. What this will do is restrict to instantons divisible by k. Let me take a minute to explain why that accomplishes an instanton restriction. So let's take the equations of motion for B here. When we take the equations of motion for B, that forces the trace of f wedge f to be k times h. H is the curvature of this. Well, locally, h is the curvature of this. That just means h is basically, if you will, an integer valued 4 form. So the fact that there's this k here means that the instanton number needs to be divisible by k. So so in effect, what Tanizaki Unzo did was add something like a Lagrange multiplier, which forces the instanton number to be divisible by k just in the most brutal fashion possible. That's one perfectly fine way to interpret this. Now, as discussed earlier, as Weinberg would observe if he were here, restrictions on instantons violate cluster decomposition, but in this case, there's a global 3-form symmetry. I can take this 3-form C and shift it by any other 3-form that is closed. So since we've got a global 3-form symmetry and we're in 4 dimensions, that means we have a global D-1 form symmetry, so we expect a decomposition. So how do we see a decomposition in this action? And it turns out it's actually pretty easy. We can just manipulate it locally. So let's take the equations of motion for C. So H is the curvature of C. Um, the equation of motion of C imply that dB is equal to zero. In fact, it implies that kdB is equal to zero. Um, you have to work a little bit harder, but you can show that B is going to be a constant. In fact, it's going to be 2 pi m over k. If we integrate out B and C3, well, B can only take finitely many values, so the path integral sums over those values. And then the result looks like the following on a connected spacetime. So this term is the original Yang-Mills action. This is what remains of these extra terms after integrating out B and C3. And you see that this looks like a theta angle. So this 2 pi m over k is what remains of B. This sum out here, this is the path integral summing over values of B. Here are the allowed values of B. And in this context, they just look like theta angles. They're multiplying a trace of FYGF, this topological term. So this is just a theta angle term in the 4D action. So the result is a four-dimensional Yang-Mills theory, a sum of four-dimensional Yang-Mills theories with different theta angles. So on the one hand, we have a 4D Yang-Mills theory with a restriction on instantons. On the other hand, we have a sum of ordinary 4D Yang-Mills theories. Separately, there's no instanton restriction, but each of the separate Yang-Mills theories has a different theta angle, so that when we sum over the contributions from the different universes, instantons of the wrong degree will all cancel one another out. That's how this sum can be the same as a Yang-Mills theory with a restriction. That sum over universes is killing off the instantons we don't like. So it's another variation on the same theme. So to recap, we started with a 4D theory with a restriction on instantons imposed just by a Lagrange multiplier condition that involved the resulting theory had a global three-form symmetry, and just by doing some very minor fiddling around, we've discovered a decomposition. So I've got more examples, but I don't know if they're relevant. Or interesting. I'll just quickly go through these. There's versions of this for non-invertible symmetries. Suppose, for example, we have a two-dimensional theory with a global rep S3 symmetry. Rep S3 is the non-invertible symmetry defined by the irreducible representations of S3. There are three of them, indexed by 1, x, and 3. And furthermore, let's suppose there's a trivially acting rep Z2 subsymmetry. So Z3 is a subgroup of S3 with cokernel Z2. So rep Z2 sits inside rep S3. And I'm going to omit all the details, but suffice to say, when you gauge variations of that, when you gauge this, what you get is various decompositions. And the precise decomposition depends upon the precise, technically the precise Frobenius algebra that you're gauging. Just talking about gauging a rep S3 is a little bit ambiguous. Here are three different possibilities for what that means, and these are the results. And in two of these cases, you get an honest to goodness decomposition into other pieces. Very quickly, some applications. The Gromov-Witten theory. The Gromov-Witten invariants count minimal area surfaces in a space. There exists a definition of Gromov-Witten invariants for gerbs. Gerbs have one-form symmetries geometrically, so a two-dimensional sigma model with targeted gerb has a one-form symmetry. Decomposition predicts, therefore, that the Gromov-Witten invariants of gerbs should be the sum of Gromov-Witten invariants of, well, spaces, I should say. And indeed, that's been checked rigorously by the mathematicians. There's an analog for quantum K-theory. Quantum K-theory can arise in physics as from operator products of Wilson lines and three-dimensional gauge theories. So here we consider a three-dimensional gauge theory with a one-form symmetry. The whole theory doesn't decompose because one is not two. But parallel Wilson lines are described by an effectively two-dimensional theory, and that two-dimensional effective theory of the Wilson lines does decompose. I just saw the question in chat. Apologies if it's been there for a while. I'm only just now seeing it. Let me pause to answer that. Um, when we add two local quantum field theories, are we describing two independent systems or one system with multiple independent interacting fields? What I'm doing is I'm really describing two independent systems, but I'm overlaying them. I'm sort of laying them on top of one another so that there's one theory, but there won't be any interactions between the two theories. This might be subtle. In most of the examples I've discussed, naively, it looks like you just have one theory with interactions. But part of what makes decomposition fun is that, nevertheless, the theory, it's possible to diagonalize the theory in some sense, so as to be able to see two separate non-interacting subtheories inside that big theory. Um, that's the way I think about decomposition. We take some general quantum field theory, which has interactions and a whole gobbledygook of stuff, and then in some sense, what decomposition is doing is, if we think of it as being like a matrix, we're diagonalizing the matrix, and then seeing how the matrix can really be cast as multiple independent subtheories that are just overlaid on top of one another. And then for the second part, in the path integral formulation, summing local actions corresponds to multiplying partition functions. That's right. That's a product. That's how you describe a product of theories. In a sum of theories, we sum the partition functions, and then in general, there's no good way to understand how the actions of those two theories combine. If we take a product of theories, it's a little bit confusing to say in words. If we take a product of two theories, we are indeed multiplying the partition functions, which makes sense with the product, and then we're summing the actions. In a decomposition, on the other hand, in a decomposition, we sum the theories, so we sum the partition functions, and then there's no simple way to build a partition function of the sum from the partition functions of the separate pieces, on the face of it. Does that make sense? Apologies if that's been up in chat for a while and I just now saw it.
I think the second question was more recent. The other one was there for like maybe 5 minutes. Yeah.
Okay, apologies, I only just now saw it.
Yeah, sorry, I also forgot to read it.
It's all good. It's all good. Well, I'm not the person asking, so maybe I shouldn't say it's all good. But I apologize for not seeing it sooner, and hopefully it's all good. Okay. Quantum K theory. Oh, good. No problem. So, quantum K theory. This decomposition story makes a prediction for makes a prediction for quantum K theory. Here, the 3D theory itself doesn't decompose. The effective theory along the Wilson lines does decompose, and in fact, you get decompositions in two different directions. And strictly speaking, it's a combination of a decomposition and a spontaneous symmetry breaking. But for mathematics, one usually is just taking some IR limit. So it looks like two copies of a decomposition. So you get a decomposition squared. Anyway, I'm not going to get into the details of this, but there's suffice to say there's a prediction for quantum K theory. My favorite prediction is for gauge linear sigma models. Let me just outline this on maybe one slide. Let's consider the GLSM for, well, I'm not certain if any of you are familiar with gauge linear sigma models. If I want to describe a complete intersection of a pair of quadric hypersurfaces on CP3, I can do that with a U1 gauge theory, with fields of charge 1 describing the CP3, and then a pair of fields of charge -2 for the two hypersurfaces, as well as some superpotential, which can be rewritten in the form of what looks like a mass matrix for the phi fields, basically because these are degree 2. Now, away from the zero eigenvalues of this matrix A, this looks like a sigma model on a CP1 spanned by the p's, because you're giving a mass to the phi fields. But decomposition says that there's actually something a little bit more subtle here. These p fields have non-minimal charges, so there's really a double cover of P1, not a single cover of P1, that's branched over the locus where that mass matrix has zero eigenvalues, which corresponds to 4 points. And that's one way to describe a two torus. So anyway, this is a simple toy model of applying decomposition to realize a geometry non-perturbatively, which is a cute trick but I love to talk about it, but it's beyond the scope of this talk. Down to some other applications, one can look at elliptic genera and pure supersymmetric gauge theories. One can apply decomposition to make predictions for the elliptic genus. Basically, you know that, well, suffice to say. And then anomalies. The Wang-Wen-Witten story is a more recent application. So very briefly, I think this is one of the last slides. If you have suppose you have a finite gauge theory. Suppose you have a finite classical gauge theory with a gauge anomaly. So in other words, the orbifold doesn't really exist at the quantum level. Wang-Wen-Witten had a proposal for how to make the orbifold work. Their idea was to make the group bigger and modify its action. They replaced the original gauge group, the original classical gauge group with the gauge anomaly, by a larger group gamma, together with and add some suitable phases, some analogs of discrete torsion, and the result was some orbifold that makes sense. That's one way to resolve the anomaly. There's something more boring you can do. You can make G smaller. If G has a gauge anomaly, then restrict to a subgroup that doesn't have a gauge anomaly. That's a perfectly fine way to make sense of these things. Turns out that these are equivalent. The Wang-Wen-Witten procedure of making the gauge group larger with this trivially acting subgroup is equivalent to, physically, the theory you get by enlarging the gauge group and adding these phases is equivalent to copies of orbifolds by subgroups of the original group. So these two options, make G bigger and make G smaller, are actually equivalent to one another. It's a fun little story. It's a neat application of decomposition in order to make sense of this whole Wang-Wen-Witten procedure, which I must confess, I found Wang-Wen-Witten's paper to be extremely obscure, but decomposition, to my mind, makes it much easier to understand. But that's maybe just a statement about me. And then finally, there's a couple of things I could say about moduli spaces, but this is a bit farther afield. So maybe just for sake of time, since I'm already almost 30 minutes over, I think I'll conclude here. So if you get nothing else out of this talk, one way to think about decomposition is that sometimes what appears to be one quantum field theory, one local quantum field theory, is secretly a sum of quantum field theories, a sum of universes. And then one can get restrictions on instantons arising from these sums, basically as interference effects between the constituent universes. And examples in two dimensions include gauge theories with trivially acting subgroups. So whenever you see a two-dimensional gauge theory with a trivially acting subgroup, at least whenever I see a two-dimensional gauge theory with a trivially acting subgroup, my first thought is, ooh, how does it decompose? And this has a variety of applications, including in mathematics, in realizing geometries in GLSMs, and various other places. All right, and I think I will stop there. Any questions?
Okay, thanks a lot for the very interesting talk.
And apologies, I went so far over, but you guys, in fairness, you guys did give me
Yeah,
permission to run
yeah,
over.
yeah, yeah. It's okay, it's okay. It was fun. It was very
Fair
fun.
enough. Fair enough.
Okay. If no one has any questions, I will ask, but let me wait because I asked already a lot.
Can you hear me? I have a question. Can I ask a
Okay.
question? Yeah. Thank you for the interesting talk. I was wondering about if you have thought to generalize what you did with U1 for the Yuan-Yang on a torus.
Oh, so
You know the instanton expression, at least on a torus, and then you can perform the same stuff. And I was wondering if you get the hard part from the U1 part of UN.
So it's I've talked about U1 theories at several different levels. If we're talking about like an UN or an SUN theory with matter that's invariant under some subgroup, like for example, suppose you have an SU3 gauge theory with matter in the adjoint representation. So that will certainly decompose. That's been worked out. And that goes pretty much just like the story at the very beginning. That's in fact, I guess I talked about SU2 theories with center invariant matter decomposing to a pair of SO3 theories. That'll happen for any SUN. For UN theories, one can ask similar statements will be true. If you have a UN theory with a subgroup that acts trivially, the UN theory should decompose. That I don't have a specific example at my fingertips, but exactly the same story ought to go through and everything ought to work. Um, there's another variation on this I've been curious about, but I don't see how to get anywhere with it. I mentioned real gauge theories versus U1 theories. Um, Something I'd be curious to see is whether there's any analog of that for a semi-simple Lie group. I don't see how. Like, is there any way to take, suppose the gauge group is GLK rather than UK. Is there any way to relate that to something else? But I don't, I, I haven't been able to make any progress with that because I don't see how to get matter that's invariant under, um, for example, some analog of a Z subgroup. I don't see how to build. Um, in other words, I mentioned that a real gauge theory, a gauge theory with gauge group the reals in two dimensions, is equivalent to a sum of U1 theories. Something I'd be very curious to understand is whether there's any examples that are analogous to that involving not just real theories, but other non-compact um, semi-simple or non-compact Lie groups in dimensions bigger than one, like GLK
Yeah.
or SLK or something like that. And the last time I tried thinking about it, I could not see a way to get started. I could not see how to build an example where something might fit together. But if it can be done, if you have any ideas, let me know. I'd
No,
be very
no,
curious to see something like that in action.
yeah, I think it's interesting too, but what I was thinking about is just like UN pure gauge theory and
Mhm.
the
Oh,
the fact that you can switch to U1 and to R with the -1 form symmetries, which is
mhm,
basically the magnetic symmetries in D equals 2.
mhm,
I was thinking if you perform the same stuff, like for example in UN on a torus, where
mhm,
you know the instant on expression,
mhm.
if you could get like the U1 part of UN to R, like you did in your paper.
Oh.
You understand what?
I think I understand what you're driving at. I don't have a simple answer, but I would be very curious to see.
Because you have basically the second Casimir,
Mhm.
and you can perform exactly what you did with the U1, at
So if
least in a
you,
torus, yeah, like because you have this n square term and the n
Mhm.
term, which is basically the theta term, and you perform the precise same stuff, and you should get the like the R
A
group.
similar story.
Yeah, 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 yeah. And
Yeah, I don't have a
that,
good example.
then you
I don't have
can
the details at my fingertips, but I
you can,
agree with
because then
your.
you can look at the topological string side, and you can start to ask what you get
Hmm.
by this story. At least that was what I was thinking.
That's so the first part of it, I don't have the first part of your question before getting to topological strings.
Yeah,
I don't have I'd have to sit down and work through examples. I'm confident that there's versions of decompositions one could apply in there. The
yeah,
connection of topological string theory is very interesting. I don't have anything to say about that, but as you're clearly well aware, Vafa and his collaborators had a
yeah,
whole
yeah, yeah.
string of papers over the years. Calling it a
Precisely.
string doesn't really do it justice, just a flood of papers over many years, talking about topological string theories and their relationship with the various aspects of gauge theories. And something I've been very curious about is whether there's any way to link into any of that. Can one take statements about decomposition and gauge theories and turn it into some statement about topological string theories? And I don't have anything to say about that, but I agree it would be I I would be very interested, and if you have if something more specific comes to mind, let's keep in touch by email. I'll put it like that. Feel free to drop me a line.
Yeah. I
I've
think
tried
that
fiddling with that in the past. I could never quite really get into it, but
I
that
think this story can work, like getting from the U1 part of UN to R, like it should work at least on torus when you can do the Poisson resummation. And
And then
then
the connection to topological string theory, that's the part where I've never
yeah, it says that
I've
on the
never quite been able
topological
to figure
string,
out how to latch
if
on
you,
concretely, but
yeah, because if you get like the instanton the zero instanton restriction, it seems like on the topological string side you should get no open strings. Basically, you can sell everything that has a like a board. So it should be interesting to look at that
so
direction.
so send me an email. I would be happy to write a paper on this. Or I suspect that there's a paper, there's probably at least one paper that could be written on this.
Mm.
I've never quite been able to get into it, but I agree it would be really interesting to flesh out those details.
And I'd also have another question, but it's just a curiosity because I'm not an expert at all.
Hmm?
If you can get like some insights from the SIMTFT procedure, because I think you can describe the composition in this context, and then you can use like the machinery that links dual the SIMTFT picture with the dual picture, and then you can get like some insight maybe on the composition too, because you can see the composition in this framework.
I think the short answer is yes.
Okay.
So this is something that Xingyang Yu, who's a postdoc here, has thought about more than I have. Xingyang has a paper where he's worked out explicitly how to describe decomposition in terms of SIMTFTs, amongst other things.
Yeah.
And I know Xingyang has thought a lot about exactly those questions, but Xingyang understands SIMTFTs better than I do. And since what you're describing sounds
Because
like
then
a
you know
part
the
of his work,
topological
I
tool.
think. Sorry?
No, I was thinking because then the SIMTFT paradigm is well understood in terms of the gravitational dual of this picture. So then maybe you can, if you understand the composition in terms of SIMTFT, and you can link the SIMTFT machinery to the dual stuff, then maybe you can get some insights on the composition, like with
It
this
sounds
log.
like a good. It sounds like an excellent plan. Since Xing Yang is the expert on SIMTFTs, and since he did the work, I
Yeah.
will. But feel free to get in. By all means, I mean, drop me a line or send me an email. Let's chat sometime, and and maybe a Zoom call with Xing Yang on the line would not be would be a good idea.
I don't know anything on this particular topic. I just
It's
that
well, a brainstorming session is also perfectly fine too. That's all good as well.
thank you very much.
Hmm? Oh, and before I forget, Midhead, I didn't realize you were here. Let me wave hi to you before I forget.
Oh, hi, Eric. I
Hey
actually,
there.
sorry, I confused the time of
Oh,
your
it's
talk, and
that's all right. I don't know if you
I
saw
couldn't
it, but I
make.
managed to give a short overview of your work with Yuya. And actually, I think your work with Mendel also wandered in here at some point as well. But you might have shown up after I went through that. But it
Uh,
definitely got mentioned.
yeah, thank you very much. I
Uh,
appreciate. I will watch your
nope.
talk, recording of your talk. But I wanted to say hi, essentially.
All good, all good. Yep.
Yeah.
I
Okay.
guess we'll see each other in or actually I guess you won't be at the regional meeting in a week, but
Yeah.
okay, I'll see Louise there and talk. Yeah, okay, all good,
I,
all good.
oh yeah. On that, I can update you. I made quite a bit of progress on the other thing we were discussing. So
Oh, okay. Well, we should Zoom sometime, or I guess
yeah,
I'll see Louise next week, so I'll talk to her, and then maybe after that it'll make yeah.
yeah, okay.
All sounds
Ah,
good. All sounds good.
okay. Yeah. Thanks for your talk, by the
Oh, it's my pleasure. My
way.
pleasure.
Sorry,
No, it's not a problem.
and I missed it.
It's all good. It's all good.
Um, I actually have a question that
Hmm?
I want to ask. So, about the U1 and R gauge theory difference. So,
Hmm?
let's first consider like the gauge theory with SUN algebra. We have many
Hmm?
different global realizations of this theory, and the
Hmm?
global realizations are given by the spectrum of line operators. but the theory is locally the same. The local operators cannot distinguish this global realization. So the way I see it, our gauge theory and U1 gauge theory are locally the same. We cannot distinguish it. Only by looking at the extended operators can we distinguish the gauge algebra. But the weird thing is, in the SUN gauge algebra, all the global realizations have the same number of, line operators. But in the latter case, we have like, in one hand, we have a real spectrum of Wilson operators. In the second, we have two spectrum of line operators, like Wilson loops of charged integer and Toft loops of charged integer. So the spectrum is not isomorphic. So this is a bit confusing to me. How do we understand this?
I think the best answer is I'm still grappling with. There are several things about the U1 versus R case that are confusing me, and I'm still grappling with how to make sense of all of it. Like, let me throw out another puzzle that's been scratching at the back of my mind that I don't understand about the U1 versus R case. And it's that in the R case, the gauge group is non-compact. And typically, often when we write down partition functions in gauge theories, we normalize by the volume of the gauge group. So in a real gauge theory, part of me wants to say that the partition function ought to be 0. Now, but there's
It's tricky. It's very
yeah,
tricky.
it's tricky. I mean, it's 0, but then you can, of course, we could always renormalize things to deal with factors of 1 over 0. So there's that option. There are at least some formal discussions. Herman Verlinde and some others described, I don't know if it's original to them, but they at least described several years ago an analog of the old McDowell-Rusakov et al. Exact partition functions for the case of non-compact gauge groups. I've been trying to figure out whether there was any predecessor paper, and honestly, I'm not certain. I've been trying to understand what limitations, if any, exist on their statements, but they give some formulas for they give some exact expressions for partition functions in the case of non-abelian gauge theories. And I actually referenced one of them when I wrote down the partition function for real gauge theory. I didn't, I should have cited that reference, but I forgot to on the slide. But it's somewhere in one of the slides when checking that when you topologically gauge the theta angle in a two-dimensional U1 gauge theory, I did some computation and got some expressions. Oh, that's the partition function of a real gauge theory. I was referencing their work. And one of the things that's confusing, one of several things that confuses me is that their partition functions are always finite, and which can be fine, which is useful for this. But I don't quite understand how to reconcile that with the idea that ordinarily in a gauge theory, we divide out by the volume of the gauge group. But maybe that's being sloppy. Maybe one should divide out by the volume of some maximal compact subgroup. I'm anyway. There are other things about just the U1 and the real case, and the real gauge theories that I'm still puzzling out. I do not feel that I understand. I do not feel like I have plumbed every aspect of that particular dictionary. And it sounds like you're raising other questions as well. So I'm reasonably confident that the decomposition works. Otherwise, I wouldn't have written a paper on it. But I also feel like there's probably more that can be said to fully plumb the depths of what's going on in relationships between compact and non-compact gauge theories. The one thing I'm confident that I do not know everything about that case. I'll put it like that. If that's not really an answer to your question so much as an evasion, but it's what it is.
Yeah. It's a bit of a hard question. I don't know how to answer it as well. I don't know. Doesn't look very. I mean, it looks like something specific to flat gauging of a continuous symmetry, or like non-finite symmetry, because when we gauge a finite one, it's always already flat. So maybe that doesn't change the spectrum of line operators, but here we can always gauge by introducing some gauge fields and doing this on a flat way, in this specific way, by saying like we don't introduce the gauge potential, no field strength, the kinetic term. Maybe that's why we lose some of the line operators. But I don't know. It's confusing.
It might be. I agree it's confusing. And this is, I need to add this to my list of things I do not understand about real versus non-compact versus compact gaugings. It's yeah, I mean, there seem to be there seem to be a lot of subtleties. That
Yeah.
I completely agree.
Yeah.
But
Okay.
anyway, let's keep in touch about this. I don't know the answer to your
Sure.
question, but I'm happy to think about it. And same goes for anyone else. If anyone has any thoughts or ideas, by all means, drop me a line. Maybe there's a paper to be written and straightening it out. I'm always game to write I'm always game to write a new paper. I'll put it like that.
Yeah. Okay. Thanks again for the interesting the talk. I don't know if there are any other questions from the chat. Maybe let's wait one more second.
Well, while waiting, let
Yes.
me thank everyone for being a great audience and for asking some fine questions. And and thank the organizers for inviting me to speak in the first place.
It was our
It's been
pleasure.
fun.
Thank you for the talk. Okay. Maybe let's take again through this. Okay. All right. Thanks
All right.
again for the talk and
Thank you.
hope to see you in the future face to
Sounds
face.
good. All right.
Yeah. Okay. Have a nice day.
You too.